we are going to talk about maximum and minimum values. It sounds familiar. It's kind of similar to the max and mean in calculus 1, right? We're going to make a connection between maximum and minimum value in function of one variable and also function of two variables. What are we going to see here in this section here is we're going to see how to use partial derivative to locate maximum and minimum of function of two variables. So in the past, we have function of one variable, and we know how to find maximum minimum using, what did we use at that time? We use the first derivative, right? However, for function of two variable, we're going to use partial derivative, and we'll see how they are different. First, let's get a picture of how maximum minimum for function of two variable look like. You see the graph over here. This is a graph of function of two variable. So it is in 3D. Think about the surface over here. And you see that this one and this one, the function value is lower than nearby function value for the function, right? So think about in this neighborhood. Okay, so if you just focus on a small neighborhood here, then the z coordinate here is the lowest. So it is a local minimum, the z value, but it is also the absolute minimum because comparing to all function value in the whole domain, this is the lowest. So that's the absolute minimum. And similarly, we can define local maximum and absolute maximum in a similar way. So if the function value is higher than any function value in a near neighborhood, then that is a local maximum. Like this one here and this one here. It's like those are the hill, okay? It's the tip of the hill. But comparing to all the function value in the whole domain, this one here is a highest. So this one here is an absolute maximum. The function value is an absolute maximum. Now, the definition for local maximum, it has a formal definition. So basically, it just say the function value f a comma b is actually greater than or equal to all function value nearby in the neighborhood. Then for some disk, okay, for some disk with a center of a comma b. So think about the things over here is, so you have a comma b over here, say a comma b, this point right here, and then you have a neighborhood here. There's a disk. Then we have a disk like this, and inside this disk, within this disk over here, f of a comma b is going to greater than or equal to all other function value inside this disk. Okay, so think about that disk here as a neighborhood, like that. Then this function value here is the local maximum. Similarly, for the definition for local minimum, as you can see here, we have a graph over here. This one, this one, this one, this one, and this one, the function value, think about it as a z coordinate. Those are all local maximum. Okay, locally, it is the highest one. But this one here is the absolute maximum because it is the highest function value inside the whole domain, within the whole domain. Okay. Now, before we do this, let's review Mach 110A. What did we talk about in Mach 110A? Remember Fermat theme. Okay, Fermat has a lot of themes, and this is one of it. Okay, this theme here says that if a function f has a local maximum or minimum at c, then if the derivative exists, then f prime of c equal to what? Anybody remember? Yeah, a lot of you said so. Yes, good job. So another way to think about this is if the function has a local maximum or minimum at c, then either the derivative does not exist at c or the derivative will be equal to 0, right? Okay, so that is going to give us a way to find local max and local mean. Okay, so we will look for local max and local mean at where either the derivative equals 0 or does not exist. Those are the possible places. just like the Easter egg hunt, right? So I said, I'm going to hide that somewhere in this room, maybe over there and there, okay? But it's going to be inside this room. So I will give you a hint, either this way or this way. And you're going to find those egg. You're going to find those local maximum and local minimum at those possible places. Okay? Remember, those are possible places, but there's no guarantee. Okay. Okay. Now, and also in Math 110A, we have a definition for critical number. A critical number of function is a number in the domain of the function. If it's outside the domain, that's not a critical number. So you first have to think about what's the domain first. And then inside the domain, you look for the critical number. And in the domain of the function, so the critical number is a number in the domain of the function such that either what or what. Looking at this, what do you think? What's the definition for critical number? Either the derivative at C will be equal to 0 or the derivative does not exist. So these two are critical number. Okay, so that's the definition of critical number. It's a number in the domain of the function such that either the derivative equal to 0 or does not exist. Okay, so remember that. So it's good to review this before we move on to Math 110C, because we're going to make a connection between this and to 110C. All right, now we go to 110C. So this theorem says that if the function has a local max or local mean at a comma b, okay, that's a function of two variables, and the first order partial derivative of the function exists there, take a guess. What should I put over here? So when you have a function of one variable, so you have the first derivative at that c equal to 0, right? But then this is a function of two variables, so we will have partial derivative, right? So we'll have partial derivative equal to what? Equal to 0, okay? And both of them, okay? Both of them have to be equal to 0 at a comma b, okay? So one-dimensional case, function of one variable, we have f prime at c equals 0. But then if it's a function of two variables, we'll have both partial derivative with respect to x and with respect to y at a comma b equal to 0. Okay, do you see the connection? Okay, all right. So this one here actually corresponds to the Fermat theorem, right? So look at Fermat theorem. The function has a local max and mean at c, either the derivative exists or the derivative equal to 0, right? And now here, if the function has local max and local mean, and the first order partial derivative either exists or the partial derivative both equal to 0, right? So there's a connection, right? There's a similarity. So the partial derivative equal to 0 over here, with respect to x and with respect to y equal to 0. Well, look at that. What does it mean? Remember the gradient, right? What's the gradient of the function? How is it defined, right? Gradient of the function at a comma b is going to be, it has two components, okay? The first component is what? Partial derivative of the function with respect to x, right? And then the second one, partial derivative of function with respect to y. And then here is at this point, a comma b, okay, that came up, a comma b, okay. So what this one's saying here is, if the partial derivative exists, then both the partial derivative with respect to x and with respect to y equals 0. So this will be 0, and this will be 0. So this will be a 0 vector, right? Okay, no, so this is a 0 vector. So which means that the gradient will be the 0 vector. So the gradient vector will be 0. So another way to say this is, you can rephrase this, okay? So then you can replace this by this. It's the same thing, okay? So if the first order partial derivative exists there, then the gradient vector will be the zero vector. Does it make sense? Okay, all right. Now we just talk about critical number, right? Critical number, remember, critical number is a number in the domain of function such that either the duality equal to 0 or does not exist, right? Now we have function of two variables. And at this time, we don't call it critical number, we call it critical point because it has two coordinates, a comma b. So it is a point. So it's called critical point or stationary point if what and what. Think about that, comparing this to function of one variable, what do you think I should put over here? If okay, so all right, so yeah, thank you. So either the partial duality equal to 0, yeah, you got it. Partial duality with respect to x, and also partial duality with respect to y equal to 0, which means that it's the same as this one right here, right? It's the same as this one. This one over here combined is the same as that one there. Okay. Or what? It doesn't exist, right? Or the partial duality does not exist. One of the partial duality does not exist. Okay. So if one of the partial duality does not exist, or both partial duality equals 0, okay, then that's called a critical point. You see the connection between the function of one variable now. Okay. Okay. It takes a while to sink in the new definition, but try to think about relate to calculus 1 to think about this. So either the partial duality both equal to 0 or one of the partial duality does not exist. So after giving this definition for critical point, we can go back to the theme and think about what it says. So it says that if the function has a local max and local mean, okay, at a comma b, then a comma b here is going to be a critical point. Okay, it's going to be a critical point of the function. Okay, so basically that's what it says. Okay, because either the partial duality both equal to 0 or does not exist. So a comma b is going to be a critical point. So I put down this two over here. So the function has a local max and mean, local max or mean at a comma b. Then a comma b is a critical point of f. So it goes this way. What about the other way? Can this one go this way? If a comma b is a critical point of the function, then the function has a local max and mean at a comma b. Okay, a lot of you shaking your head, so you say no. Yeah, it doesn't. Okay, it only goes this way. Okay, so for function of one variable at that time, we also have a similar case. If the function has a local max and mean at c, then c is a critical number. But if c is a critical number, there's no guarantee that the function has local max or mean there. Think about x to the third power, right? So this is a function x to the third power over here. If you differentiate that, we get 3x squared at 0 over here. What's f prime of 0? That's equal to, substitute 0 in x, we get f prime of 0 equal to 0, right? Now f prime of c equal to 0. Do you think the function value at 0 here is a local max and mean? No, it's neither, right? So there's some value below that, there's some value above that in the neighborhood, right? So definitely this is not a local max and mean. So it only go one way. So if it's local max and mean, that's a critical point. If it's a critical point, not necessarily it's a local max and mean. Now let's try some example over here. This is a function of two variables. Now we want to find the max and mean. Let's find the local max and mean first. But in order to do that, what do we need to do? We need to actually, we should actually think about the domain first. So what do you think is the domain of the function? The domain for this function, is this a polynomial function? Yeah, so the domain will be all of R2, right? Okay, good. So there's no restriction on x and y. Now we're going to take partial duality. So then we can find critical points. Just like we take first derivative to find critical number, we take partial derivative to find critical point. So let's take the partial derivative with respect to x here. Partial derivative. So when you take partial derivative with respect to x, this one here is with respect to x. Then think about the x over here as the only variable, and all others are constant. So just focus on this chain and this chain. What's the derivative of x squared with respect to x? 2x. So, and then here we look at the derivative of that is -2, right? So we should get 2x minus 2. Now we're going to take the partial derivative with respect to y. Now we're going to focus on the y. Okay, so those chain has 1. And then we just take the derivative of those with respect to y. What should I put here? 2y minus 6. Yeah, good job. 2y minus 6. Okay, good. Now, in order to find critical points, we're going to set both partial derivative equal to 0, right? If I set this equal to 0, what does x equal to? 1, right? Okay. And if I set this equal to 0, what do I get? 3. So the only critical point is 1, 3. Okay, that's the only one. Now we find the critical point. Let's complete the square. Okay. Now it's a good time to review how to complete the square. Okay. Do you guys remember how to complete the square? I'm going to give you a review how to complete the square here. So to complete the square, over here we have 2 variables, x and y. So first we're going to put the term that has x in one group, and then we're going to put the term that has y in another group. Okay, and then I can leave the number at the end. Okay, now let's think about what to add. What number do I need to add here in order to make this a perfect square? And then what number do I need to add here in order to make this a perfect square? Okay, let's do that first. And then, okay, what number do I need to put here to make this a perfect square? The perfect square formula, if this leading chain over here, the coefficient of x squared here is 1, then you would take, remember what is x minus b squared, right? That's x squared minus 2bx plus b squared. And you see that when the leading coefficient here is 1, this one and this one are related this way. This is half of this. You get the b, and then you square and put it at the end. Then this is the perfect square of x minus b. So we're going to do this. So we're going to take half of -2, which is -1, and then we're going to square this. So we'll get 1. So if I put 1 there, then that will become a perfect square, right? Now let's do a perfect square also for this to complete the square for the y term. This is y squared minus 6y. What number do I need to put there? Yeah, that's 9, right? So you take half of -6 and then you square and put it here. That number is going to make this 3 chain here become a perfect square. Now before, but I'm adding 1 and 9. They were not there before. So at the end, I need to subtract back, right? So what do I need to subtract at the end? We subtract 10 at the end. Okay, so I'm not adding anything extra. So I add 1 and 9, and later on I subtract 10. Then this expression is the same, is equivalent to the expression that you start with. I'm not changing the value. I'm not adding any extra. Okay, so I'm just completing the square here. Now, according to this, now we can write it as a perfect square, right? What perfect square is this one? That's the perfect square of x minus 1 perfect square, right? And then this is the perfect square of what? Y minus 3 perfect square. And then at the end, what do we have? This is going to be 4. So we add 4 to it, right? So that's how we complete the square. Now, just like the parabola, okay, this one here is a square and this is a square. Those quantity will be greater than or equal to 0. So what is the minimum? What is the smallest function value f of x comma y? That will be 4, right? So 4 is a local what? Max or mean? local minimum, right? Okay, so in any neighborhood here, okay, 4 is the local minimum. But it's also the absolute minimum because in all of its domain, 4 is the smallest function value. So therefore is the absolute minimum also. So first you say, okay, it is a local minimum, but it's also the absolute minimum. And we can confirm the result we have here by looking at the graph of this function of 2 variables here. And this is a graph, okay? It is an elliptic paraboloid. And when x and y equal, when x equal to 1, when y equal to 3, the function value is 4. Okay? And that 4 is the smallest function value in the whole domain. Now let's look at example 2. Example 2, we try to find the extreme value of the function y squared minus x squared. Now, in order to find, what do you mean extreme value? Extreme value means absolute max and absolute mean. So this is what it means. In order to do that, we need to find those critical points, right? And to find those critical points, we need to take partial derivative. So we're going to take partial derivative with respect to x here. And that's not hard, right? What's partial derivative this with respect to x? That is negative 2x. What's partial derivative of this with respect to y? 2y. Okay. Now we're going to set the partial derivative, both of them equal 0, to find critical point. Okay. So to make this equal 0, x equal to 0, and this one here, y equal to 0, right? Okay. So the only critical point here is 0, 0. Okay. So we found a critical point. Do you think this critical point gives you local max and local mean? Let's find out. Okay. So I'm going to consider point on the x-axis. Now notice the domain for this function is going to be all of R2, right? There's no restriction on x and y. Now let's try to consider those points on the x-axis. Okay. So let's try to think about this. So x-axis, y-axis, and then the z-axis. Now we're going to consider all those points on this x-axis over here. Okay. On the x-axis, the y-coordinate will be 0. Okay. When the y-coordinate to be 0, we can actually replace this. We can replace this y over here by 0 on the x-axis. Then the function here is going to become a function of one variable only, which is the function equal to negative x squared, right? Negative x squared is negative. If x does not equal 0, then it is negative, right? It's a negative quantity. So what does it mean? On the x-axis, for those points on the x-axis, the function value will be all negative, except at this one. At here, it will be 0. Okay, but here and here, the function value will be negative. So maybe I can put it this way. So should we have negative here and negative over here, on this side and on this side. Now, the second time we're going to focus on points on the y-axis. So now on the y-axis, if it's on the y-axis, then x is going to be equal to 0. So we're going to replace this by 0. Then the function will simplify to y squared, which is going to be a positive quantity if y is not 0. So what does it mean? So we're going to have positive and positive over here and over here, the function value. Okay, and then at 0, 0, that will be 0. Okay. Now, do you think the function value at this point 0, 0 is a local max and local mean? And what's the reason? Give me the reason. Is it a local max and local mean here? No, because you have nearby value are positive, right? And then also nearby value are negative. Definitely that cannot be max or mean in that neighborhood because there's some value that's greater than that. There's some value that's less than that, right? The function value at this point here is actually 0. Okay, it's going to be 0 over here. But then there's some value greater than 0, some value less than 0. So definitely 0 is not a local max and is neither a local max nor a local mean. Now someone will say, wow, Is that a little bit tricky? Well, a lot of time in math, you try to think about it. We do to a simple case first. So you can try to think about along the x-axis, along the y-axis, what happened, and try to think about it this way. Now, here's a visual picture of the function, like that. See, the function value here is actually equal to 0. That's equal to 0 over here, okay? And along this x-axis, you see the function value are negative, okay? It's below 0. Along this y-axis, the function value are positive, okay? Except over here, okay? So you see this is neither a local max nor a local mean. It is actually called a saddle, okay? So 0, is called a saddle point of the function. Does it look like a saddle for you guys? Remember the horse or saddle, right? Okay. So then we have a saddle point over here, okay? So this is one example that when you have critical point, the function value is not necessarily a local max or local mean. And you could have a saddle, okay? You can have a saddle like this. Next, we're going to talk about the second derivative test, okay? But let's review the second derivative test for function of one variable first. Like 110a, we talk about the second derivative test, okay? Now you guys want to remind me, what does it talk about? Suppose this second derivative is continuous near c if the first derivative at c equal to what? You guys remember? Equal to 0. And if the second derivative at c is what? Positive? Oh, good. And I remember some students from my math 110a. Okay, good. Yeah. I always love to have students from my math 110a. Okay, so it's positive. Okay. Then if it satisfies this, okay, well, let's think about the picture. If f prime of c equals 0, so you're going to have a horizontal tangent here. And then the second derivative is positive, okay, near the c. So near the c, we're going to have concave up curve. Then the function value here is a local what? Minimum. Yes, good job. Okay. And similarly, if f prime of c is equal to 0, and if the second derivative is negative, then the function value will be a local maximum, right? Okay, good. So that was the second derivative test in 110a, calculus 1. Now we're going to have this second derivative test in 110c. What does it say? So suppose second partial derivative of the function are continuous on a disk with the center a comma b, and suppose both partial derivatives equal to 0 at a comma b, okay? Which means that a comma b is a critical point of the function, okay? Then what happened here is we're going to look at the d, okay? Look at the d over here. If how is this d here defined? It's defined this way. Now you might think it's a really long expression, but one way to remember this expression over here is the determinant, okay? So you can get this determinant like this. So you have fxx here, and then times fyy right here. Subtracting here will be fxy, and here will be fyx. So what do they mean? This means partial derivative with respect to x, and then with respect to x again. Second order partial derivative with respect to x and with respect to x. This is second order partial derivative first with respect to x, then with respect to y, etc. This one over here actually corresponds to the symbolic determinant of this matrix. Okay, so you have fxx times fyy, subtracting fxy times fyx. Now, but here it says fxy. What's the reason? Why? Why is that? Yeah, because by corrosive, fxy equal to fyx, if it satisfies that, those conditions, and all the function we encounter here they all satisfy that condition, right? So these two are equal. So these two are equal. So that's why they put fxy here. So it's this times that, subtracting this times that. Okay, so that is the D over here. Okay, now what happened here is if D is, these two cases is for D is greater than 0. The last case here is for D is less than 0 at, okay, less than 0 at A comma B. If D is greater than 0, we have two cases. If fxx here at A comma B is positive, or was negative, that is case B. Okay. Let's try to kind of relate to the second derivative test for 110A. This one kind of play the role like the second derivative. So if this second order partial derivative with respect to x and x again, if it's positive, kind of think like the concave of things, then the function value will be a local minimum. And if that is positive, kind of think about like it's like a concave down graph. Okay, and the function value will be a local maximum. Okay, so it's helpful if you can relate this to calculus 1, the second derivative test, and that will make things a little bit easier to remember. All right, so that's how I remember this too. Okay, if the D here is this one over here is less than 0, then what happened here is the function value is not a local maximum nor a minimum. Okay, and the situation here is A comma B is going to be a saddle point. So neither, and that is a saddle point, just like what you see in the picture, right, in the graph. Question? All right, so that's the second derivative test. Okay, let's make some note over here. The last case over here, remember when D is negative, then A comma B is a saddle point. Okay, here is two visual picture of the saddle point. Okay, so the graph of the function actually calls its tangent plane. See the brown plane over here? This is the tangent plane. The second note over here is if D equals 0. So the three cases here is when D is positive, when D is negative, but they didn't talk about when D is equal to 0. When D equal to 0, the second derivative test gives you no information. Just like the second derivative test for function of one variable, it didn't give you any information, remember? Okay, so it doesn't give you information. And the last note over here is the way that we remember the D is to think about this, the determinant of this matrix right here, the symbolic determinant of this matrix, okay? And that's the way to remember that.